So games are really well-defined problems nested in ill-defined problems. Let me talk through that a little bit. So games are well-defined problems. Well-defined problems are problems that have edges, that have clear rules and boundaries, that are constrained in a certain way so that you know when you hit the right answer, and the answer that's correct is not ambiguous. So for example, algebra problems are well-defined problems. Another example of a well-defined problem is something like the Tower of Hanoi. Kind of popular kids game, very highly studied, where you're trying to take discs on one peg and move them to a third peg in an order so that no larger peg is on top of a smaller peg. What's interesting about this kind of problem is that, again, you know when you've come across the answer, there's typically one right answer, and it's not ambiguous. It doesn't require a lot of interpretation. Well, my background is cognitive science, so I was trained and have spent my career studying cognition and learning of human beings. And in early cognitive science, we were all about problem solving and problems that were very well defined, like the Tower of Hanoi. So these are problems where you can actually map out every possible state and every possible move that a person could make in the problem. Then you could map how well a person traversed that problem space and whether or not they solved it. If you can map the space, it's a well-defined problem, even if it's a big, big problem space. Now, in cognitive science, a lot of what we did for a very long time and still continue to do in certain realms is to build these computational models of cognition, of players solving well-defined problems. So we would build programs that would solve problems like the Tower of Hanoi or algebra in the same pattern that would mimic an adult, mimic a child, that would mimic problem solving from humans. And once you do that, if the computer program can predict what a child does solving algebra, then you've got some basis for arguing that, in fact, the computer program must in some way be a good model for cognition in the head itself. So increasingly, we had this sort of metaphor where the mind was a computer. You had input information, you had outputs of behaviors, and then inside was symbolic processing, right? The computation of code. Now this works well. Our folk theories of psychology really support this sort of idea. I mean, I find myself saying things like, I'm sorry, I just don't have enough bandwidth right now to actually process what you're doing, what you're talking about. Come back later, right? So metaphors in typical American society sort of support this sort of ideas, but it runs into some problems eventually when you start looking at problems that are more complex, and I would argue more interesting problems than something like the Tower of Hanoi. So at that point, when you deal with something like, for example, how to write a 5-paragraph essay, what's a good article on the American economy, you start to have to ask questions about interpretation that make those kind of problems, that kind of computational model of problem solving, much more difficult. And a lot of times what you end up doing with an information processing model is to say that social and material contexts are sort of a wrapper around the problem-solving environment, right? Why does that matter? Well, think for a minute about the difference between solving an algebra problem with your computer versus without, with a calculator versus without, with an abacus versus without, with a simple piece of paper and pencil versus without. It turns out that tools literally change the way that we're processing information in our heads. Part of the processing of what you're doing cognitively, when you use a tool, even as simple as paper and pencil, is using those external devices to be part of your computational apparatus. So suddenly the material world becomes part of the unit of what you have to study. But a typical computational model of cognition doesn't even include that. Now imagine that you add a social context. A social context is going to give you a whole nother level of complexity of what you have to take into account. Mostly because the social context tells you what the meaning of the symbols are. In order to take account of human cognition and learning, you have to start taking account of an embedded, situated view of cognition. And what do I mean by that? I mean something like what Jean Labe defines as cognition, as a complex social phenomenon, distributed, stretched over, not divided among mind, body, activity, culturally organized settings, which include other actors. Now, games are a really interesting space to look at cognition in this way. If you want to study embodied cognition, socially and materially situated cognition, games are a really compelling context. Let me give you a case in point. So I've spent a lot of time studying massively multiplayer online games. And a classic kind of activity in massively multiplayer online games is your typical dungeon raid after a boss or mini-boss. So you have this well-defined problem where a team of, let's say, 4 people goes out to conquer a mini-boss. You may have a healer, a tank, and 2 damage dealers. That's a typical kind of arrangement or configuration of players going out to solve this hard problem. So fairly well-defined. You've got 4 particular operants in the event, and then you can start asking yourself questions about things like what is the appropriate and most efficient type of equipment or materials or team configuration that would actually solve that boss monster the fastest. That's a well-defined problem that you could map the space of, you could build a computational model, and discover what is the most efficient pathway to the solution of solving the boss monster. But now think for a minute about the question of what does it mean to be a good tank, right? What does it mean to be a good healer or a good damage dealer in this kind of game? The actual question, the problem of what it means to be a good tank, is not merely solving the problem most efficiently or knowing what configuration is actually the right or most appropriate configuration for solving a given boss monster. It also means that you have to be able to argue well, you have to be able to present yourself on forums, you have to be socially recognized as an efficient tank, for example, not being a jerk in group so that your group falls apart. So it takes more to actually be a good tank or a good healer in a game than simply solving a well-defined problem. So if we take a situated point of view of cognition, which I would argue we have to if we want to account for complex human performances and human learning, if we take that view of cognition, we have to consider not just the well-defined problems that participants and people are actually solving, but the ill-defined problems of interpretation that they're solving at the same moment. Games are a particularly great space to look at this because they are a configuration of very well-defined problems nested inside ill-defined ones. Game fandom and community render game as designed experience meaningful. It's where you see some of the most higher forms of human argumentation and collective problem solving in the game-related spaces. So when we talk about games and learning, we need to consider not just the game as a designed experience, as a designed object created by developers to challenge players, but also as a game fandom space, as a community that functions in very particular ways to serve as a community for learning in and of itself.